Hi everybody, is it close enough? I think so. So I'm Boyé. I'm doing my thesis with Mario Merino, who just left, and Guillaume Navarro on the prototype development and testing of the magnetic arch thruster. I've begun 1.5 years ago here in Madrid in January 2021, and very soon we'll be able to manage to have the thruster I'm presenting ready. More or less, I'm going to split my presentation in 4 main parts. I would like to give a quick introduction on electric propulsion and also electrodeless plasma thruster, which is the type of thruster I'm actually using now. Then I will quickly go on the Zarathustra project, which is the one I'm working with Mario, Diego, and Davide, which are in the audience. And then we'll go to the summary of the preliminary work I've been doing in the last 1.5 years. And we'll conclude by the thruster development and the assembly for the first ignitions, which will come today, let's hope for this week at least. First, Enrique have made the introduction on electric propulsion, so I'm quite happy about that. But I will just add that these electric propulsion main thrusters, the traditional ones, they are limited by the presence of an electrode inside the plasma. So it limits the lifetime first, and also it's creating some inability to adapt to power scaling. Thus, we also have to use what we call a neutralizer, which is usually a hollow cathode, in which you can see, I don't know how to point with this. You can see here it's a hollow cathode, which is actually making the bridge, the plasma bridge, to generate thrust. And this neutralizer, because of its functioning and because of the heating, it's a critical component, and also it limits the use of some other gases such as argon or krypton, because you have to use xenon in order to avoid contamination of the insert used in the cathode. Now, what's an EPT, so electrodeless plasma thruster? Very quickly, it's a thruster, in which the plasma is created thanks to a microwave injected by an antenna, and is carried out without any electrodes in the plasma, just by a magnetic field which is confining the plasma and carrying the plasma out. As you can see, here we have a waveguide. This is more or less the scheme of classic electrodeless plasma thruster. We have a waveguide in which we input a microwave, and which is hitting the plasma here with the help of the coil, which is here and here. I mean, it's a slice. And this plasma is then carried out by the magnetic field out of the thruster itself. This is allowed, and we are using, and also this is allowed in the scheme, by the electron simultaneous resonance, that we call ECR. Basically, in a magnetic field, electrons, they have a circular motion due to the Lorentz force, and when this motion is overlaid by an axial motion, it transforms into a circular motion. And then the plasma is created and carried out by the magnetic field. So the plasma generation is allowed and enabled by the collisions between electrons and neutrals. Now, what's Zarathustra? It was a prototype of thruster imagined by Mario Merino, and which is more or less what we see here. So with this U-shaped ionization chamber and with some magnetic arch. This is what we call it, the magnetic arch thruster. The goal of this electrodeless plasma thruster is to have a generated magnetic field which is everywhere parallel to the thruster wall. So we are not colliding with a real plate. As you can see here, the plasma also is colliding with this real plate. And by having this U-shape, we have the plasma going all around the U-shape and going out, so we don't collide with the real plate as we do with classic EPTs. And also the magnetic nozzle is solving the issue of the magnetic nozzle divergence, because we have now a closed line magnetic field. And so we are solving this divergence of the magnetic nozzle, which is actually carrying out the plasma in some directions we don't want. Thanks to that, we can reduce the plasma losses theoretically to the walls up to 50%. We'll see that with the first prototype. And we can lower the plume divergence, as I've said before. Maybe, and we'll see that in the next prototypes, we'll be able to allow first vectoring by just controlling the magnetic field, which would be quite a big step for space propulsion, as we will not have some moving parts as we have now. How does the first prototype works? As you can see here, this is a rendering we have made some months ago, with the coils sorted out all around the ionization chamber, that we see actually a tube inside them and a main part here. So basically, the gas is injected on the back of this main part. You cannot see it in this rendering. You will be able to see it in some pictures next. And we are injecting power, so microwave power, by this coaxial entrance here. So then, when these cars will be heated and will be transformed into plasma, thanks to first the microwave injected and also the coils and the magnetic field generated by the coils around, and the plasma will be confined and carried around, carried out, of the thruster and of the ionization chamber, thanks to these two exhausts and these two big coils, which are called the magnetic nozzle coils. We, in the preliminary work, we have decided to decompose our project into, let's say, three main subsystems. First, the coils, because we have to generate the sufficient magnetic field to carry out the plasma. And also, we decided to focus on the power injection of the transmission line, because it's a sure thing, it's tough to bring this microwave from a generator to the thruster without losing that much power or without leaks. And then we had to make a complete CAD to make the first prototype. But the thing is, even though we decided to split this subject into three subsystems, let's say three main subsystems, it's a sure thing that they are all linked all together, one to another, in the sense that by changing the coils, let's say the current in the coils, we have to change the thruster itself, so the ionization chamber, because we'll have to change magnetic topology. So everything is linked, and we had to make some trade-off to more or less ensure coherence in the project. Very quickly on the coils, because that has been a major part of my work, I've been using a MATLAB code in order to study the magnetic topology inside the thruster. And it has been decided to split the coils into 10 little coils, which are actually all around the thruster, as you could have seen before in the rendering. The thing is, the ECR phenomena to produce plasma, we had to get a magnetic strength, which is actually the one you can see in red with this resonance line, of 875 Gauss in order to ensure the production of plasma, because we're working with a microwave with a frequency of 2.45 gigahertz. So with a radio space, because we don't want the thruster to be very big, with such a radio space and also with such a weird shape, we had to fit all the coils and to generate a sufficient magnetic field to ensure the plasma production. It was a tough job, but with simulations we achieved to optimize the coils repartition. Then we moved to the power transmission. We made some analysis upon the transmission line and also upon the electromagnetic simulations in the thruster itself, in the ionization chamber, in order to see if the wave is evanescent or is resonating inside the ionization chamber. Sorry. So we chose actually to use a coaxial transmission line, because we can go up to 1 kilowatt, which is something which is a bit harder to do with waveguides. And also we wanted to ensure we will not have any leaks with waveguides that are usually used for this kind of thruster. We also used some solid-state microwave generator for stability and efficiency. And with all this transmission line, we could make some analysis in order to determine first the leaks and also the losses of each element in order to see more or less where we could have flows in our system. And that led us to the thruster development and assembly with the ordering of and procurement part and the ordering of all the parts of the thruster. As you can see, this is an image of which was taken during the assembly with the alignment with the laser cross. The thing is, we had to measure the tolerances, the offsets, and the alignments of every element, because it's a really tight thruster, and some offset of even some millimeters could have been way worse than what you can imagine, because the resonance line would have moved inside the thruster. And so in the end, it's a very tough job to make the assembly and to have everything ready and set. This also because some of the parts we've been ordering, they were made customized, and so sometimes they are going beyond allowed tolerances, so we had to correct that as well. We also made the probing of every coil, because obviously the manufacturers, even though they are very good, they cannot ensure that we'll have the exact number of turns per coil, and also the central magnetic axis is not always aligned with the geometric one. So we have to make the probing of of every coil with some probes. As you can see here, this is like the probing of the central axis with the magnetic field probe here. And to have the correction first in current and also of the axis, in order to ensure that we have this correct line, as I've shown before, this red line, to allow the generation of plasma. And to finish before the main assembly, we have made some analysis upon the transmission line, as we expect to have obviously some losses and some leaks. As I mean, no real system is perfect, so we'll obviously have these things. We use transmission line theory, to determine the losses implied by each transmission line elements, and also in the end we conclude that we will lose almost 8% of the power forward by the generator to the thruster, because of the presence of some critical components in between, such as a feed through, because we're using a vacuum chamber, as you can see here. The thruster here is placed in the vacuum chamber. Actually, this was taken yesterday, so it's quite recent. We had to make what we call ICD, so the interface control document, to see if we have some critical interfaces in the system, to identify them and to work around them in order to be sure that when we'll put the thruster in the vacuum chamber, everything is set and ready. Because the thing is, it takes more or less 1 day to have complete vacuum and to be ready to operate. And once you close the chamber, well, you cannot open it. So you have to be sure that when you close it, everything is fine. So as I said, the installation has been made yesterday, and the ignition is aimed, the attempt at least is made for today or tomorrow. We'll see how it goes. And this represents actually quite a milestone for us, because it has been 1.5 years we've been working on it. Diego is making simulations, David is making some data analysis methods. So it's a very big step, as the thruster is actually the main component of this project. And the results of this first ignition will be presented by Mario with also Diego in IAPC, the International Propulsion Conference in MIT next week. Now, the next steps. Obviously, we'll have to analyze the first ignition outcomes, because it's one big step for us. And then we'll see if we have to improve the first prototype or to make a second prototype by correcting some flaws of the first one. And then we'll be able to define, well, the first test campaign. Then some analysis of this first campaign will give us some data about the plasma, some data about the thermal behavior of the coils, because they act really differently in vacuum or in the atmosphere. And also we'll be able to analyze more or less what's going on in the microwave transmission line. And it will help us understand the behavior of the antenna and also the plasma generation. And everything would be put in some publications, so the first ignition and the first test campaign, which will be presented in conferences such as next week, and also in some journals. So these are the big main steps, and for now we are proud to say we'll attempt to ignite today, if in the evening, or tomorrow for the first time, a 1.5 year project. So we are quite proud, and I'm quite looking forward to have an ignition, touch wood, or maybe not, but at least we'll have some results. Thank you for your attention, and if you have some questions, also the references.